So today I'm going to basically focus on the the handout on probability. So let me share something about that. Um, right. So yeah, you're going to have to read this and ask some questions about this for your final assignment. Uh, there will be a couple of there might be some questions on these issues on the final, but obviously, I mean, it's proportional to the amount of stuff that we devote to it. So obviously, but anyway, so the basic idea is we have been discussing so far deductive inferences for which we have been using logic to understand how, when we have some information, we can make deductions from that information. So that information, we often call that information premises. And then if the premises are true, and we use, principles of inference of valid principles of inference, such as the ones I gave you, which are logical truths, then you should be able, from those premises or those facts, which are true, make correct deductions. So infer other true facts by pure logical reasoning. However, sometimes we want to know, we want to find out whether some facts or some information we have, or what, usually, I mean, the term for premises in when talking about probabilities they are usually called evidence. So so for example, in logic, we use the term premises and term conclusion and talk about the validity. But when we are talking about probability, we talk about evidence. We talk about how much that evidence supports a hypothesis. That's going to be the inferential relation in this case, taking that evidence or those facts that we find out or know, and then figuring out if those facts hold, how much do they support some hypothesis. So that's the sort of interest we have in probability, and it mostly has to do with the support of inductive inference. And again, I mean, just for the record, I should just mention that obviously we have very formally developed and precise notion of probability in mathematics, which we apply to understand how these sorts of inductive inferences work. But that doesn't solve the problem of induction that was discussed last time, the philosophical problem of induction. And part of the reason why it doesn't is because the only way in which we can use these probability rules to make inferences in many of these cases is by assuming that the future is going to be like the past, so that there's going to be, what Russell mentions about the uniformity of nature, so that information that we have about the past can serve as some sort of inductive basis from which to make probability judgments. So usual, I mean, the future so far has resembled the past, so it seems reasonable to use probability in that respect, but that of course does not solve the philosophical problem. But we certainly have to make inferences, right? So we have to make some assumptions. In most cases, we have to make some assumptions, right? So even in logic, for example, which is, as I mentioned, is for example, in logic, I mentioned that, for example, if you have the premise P, and you know that it's true for a fact, and you have the premise that P implies Q, and you know that that's true for a fact, then by the rule of inference or principle of logic modus ponens, you can deduce Q, and you're going to know that it's true for a fact. So, and you can, use truth functions, as I explained in some of the lectures on truth functions and that handout. You can use truth functions to show, like as a matter of computability, that if you have P and you have P implies Q, and those are true, then Q is going to have to be true, right? So in that sense, in logic, there's this, there are these facts that hold just by pure logic, but it doesn't mean that there aren't. That does not mean that there aren't any assumptions. So, for example, specifically, something which is specifically very important in logic is that we are presupposing that there are only two truth values and that they are mutually disjoint. So, for example, in logic, one of the assumptions we make is that every proposition must have a truth value. So every proposition must have a truth value, and that truth value must be either true or false. So it must have a truth value. It can be one of only two truth values, and furthermore, that it cannot have both of those truth values. I mean, that seems very reasonable given the fact that we cannot even imagine what a contradiction will be like. But that certainly built up into the idea of how we use truth functions and who we use and the way in which we use logic, right? So, so it seems like some sort of inductive inference having to do with the fact that the future is going to resemble the past is pretty much also part of our basic assumptions about the world. It allows us to make empirical inferences whenever we have some information. So, so again, and we should start out by just describing what are the principles of probability. So just as I described what were the principles of logic, and analogously, just as we discussed when, for example, when we were looking at some examples of mathematical structures beforehand, like the piano axioms in the case of the Russell's Introduction to Mathematical Philosophy, those are principles that hold for the natural number, truths of the natural numbers, that such that, for example, if you have those, the piano axioms, you can find out or deduce the truths about the natural numbers. So different mathematical domains have different principles or truths that hold about those domains. And we use these principles to make deductions about what, about the nature of those domains, right? So for example, in the case of, again, in the case of logic, we have the rules of inference I gave you. In the case of natural numbers, we have the piano axioms. In the case of probability, we have what are called the Kolmogorov axioms, because he's the one who introduced these axioms. And obviously, the real numbers have their own axioms and so on, right? So that usually happens with mathematical structures. We can distill the basic assumptions into axioms and then use those axioms as premises in a way to make deductions. And those are going to be called theorems of those mathematical theories. But in real life, that will be analogous to the relation between premises and conclusions in deductively valid arguments. So one of the things I mentioned was that for this handout, you need to watch, in order to read it successfully and understand what most of it says, you need to watch the lectures, Basic Set Theory 1, which I recorded like months ago, the one on Basic Set Theory 2 on relations and functions, and the one on logic and truth functions. So all those three are necessary for this material and the material next week, okay? So we're going to start out with the structure. So this is our structure. It's an ordered triple of sets. So this is just like a way of representing different sets different sets and mathematical objects that are going to be important to understand probability. This is the Greek letter omega. So this is going to be a set. We're just going to call it omega. That's going to be called our outcomes, our possibility space. So that's going to be, for example, so suppose, for example, that I'm going to give an example in a second, I guess, but so that's going to be our possibility space. Then P omega, that's how we are going to read this notation here. That's just going to be the power set of omega. So the power set, as I defined it previously, is just the set of all subsets of omega. And then small p is just going to be a function, the probability function. And that function is going to assign a real number. So, with the real numbers, what are the real numbers? Just a brief callback to that. The real numbers are just the the rational numbers and the irrational numbers. So for example, stuff like fractions, 2/3 or 1/5, which are equivalent to 0.5, 0.3, stuff like that, plus stuff like the irrational numbers like square root of 2, etc., etc. So that's basically what the real numbers are, just all of those numbers. So it's going to, this probability function small p is going to assign a real number between 0 and 1. So it could assign, for example, 0.1, 0.2, 0.33, 0.33, something like that, to an element of this. So to every subset of this set, which are the elements of this small p is going to assign a number. I'm going to give you a more concrete example in a second because I know it sounds very abstract. And all of this triple is called the probability space. Okay, so that's and this structure here, that's what obeys the axioms, the Kolmogorov axioms, which I haven't mentioned, but I'm going to mention in a second. So again, here's an important difference with logic. In logic, any proposition is assigned either one of two values, which are exclusive. It can be assigned true or it can be assigned false. And for the sake of this, the sake of this discussion, we are going to identify true. The value true, we're going to identify that with the number 1, and we're going to identify the value false, and we're going to identify that with the number 0. So in logic, we only have two values, 1 or 0, true or false, and there's nothing in between. So a proposition from the standpoint of logic, we can only consider that as either true or false, full stop, right? In an absolute manner. But in probability, we don't do that. In probability, we consider how likely some proposition is, or how likely some event is. So it might be completely certain, in which case we think of it as having probability 1, or it might be completely certain that it will not happen, in which case we think of it as having probability 0, right? So for example, any contradiction has probability 0, for example, right? So for example, the fact that I'm sitting here and I'm not sitting here at this time, at the exact time, that's impossible. So since it's impossible, it has probability 0. And what are called actually the laws of logic, for example, the law of the excluded middle. So the fact that I am either sitting here right now or not sitting here right now, because that covers all the possibilities, the logical possibilities. So either I'm identical to Moises or I'm not identical to Moises. All of those are instances of the law of the excluded middle, of the form P or not P. So all of those, so the law of the excluded middle is what is called a tautology. So something which is always true, a principle of logic. So a proposition that is true in all possible worlds, necessarily true, etc., etc. So tautologies have the maximum likelihood of 1. They are always going to happen. They have the maximum probability. Those are some examples. I'm going to give you more, other more concrete examples in a second. This is just like a technical notion of how we call these triple. They are called sigma algebras. That's not going to be necessary for anything you do for the exam or anything like that, but it's just like a cultural, like a trivia stuff that I put in there. So yeah, so we're going to call, again, omega the possibility space or the sample space. And then we're going to call elements of P omega, we're going to call that events. So for example, we want to use probability to, for example, measure how likely is the outcome of an experiment, okay? So part of the idea is that when we're thinking about an experiment, we're thinking of what will happen if, if there are these possibilities and we perform some sort of experiment on them, then what will happen? What will be the final result, right? So for example, suppose you have, as in here, suppose you have a die, right? And you want to find out what's the likelihood that it will fall on 1, for example, right? So the possible outcomes, which is going to be omega, for that experiment specifically, for again, for every this, this abstract structure here is going to represent the probabilities of an experiment for different experiments. So you have to interpret what these things mean in the case of each experiment. So in this specific case, the experiment is throwing a die and what I want to find out is how likely it is that it will fall on 1. That's the experiment. So the sample space or the possibility space here, omega, is going to be this set here, the set of possible outcomes. So it will either land 1 or 2 or 3 or 4 or 5 or 6, right? So that exhausts all the possibilities for the die. Then what will P omega be in here in this case? So let me. So we have so remember that the power set of a set is the set of a set A is the set of all subsets of A. So, and A is a subset of B for any sets A and B, so arbitrary sets. If and only if every element of A is an element of B. So what will be the subsets of this set here? So, again, a subset is just going to be any set such that if, for example, if X is in that set, then A is going to be a subset of B if and only if X is in A, then X is going to be in B. So for example, notice that this set here, so is one, so I'm just going to call this again I'm just going to call this omega. I don't have Greek, I don't know how to write Greek letters with this. I don't think it's doable for this, this part of Zoom is not very sophisticated, but so, and this set here, I mean, this is called the singleton of 1. It's just the set that has 1 as a member. So for example, the question is the singleton of 1 a subset of omega? Yes, it's a subset of omega indeed, because every element of, in order to be a subset of omega, then every element in that set must be in omega, right? So 1 is an element of the singleton of 1. Is it also an element of omega? Yes, it's here, right? So that means that yes. So and by the same reasoning, by the exact same reasoning, all of these are called the singletons, because every set that has only one member, that's called a singleton of that member. So the singleton of 2 is that a subset of omega? Yes, for the exact same reason, right? So 2 is a member of the singleton of 2. 2 is in here, and 2 is in omega, right? So it's also a subset of omega. And so on, so on. These are also there, right? So 3 is there, 4 is there, 5 is there. Sorry. 6 is there. So these are all elements of P omega. So the second element in the structure. So these are all elements of the power set of omega, right? Because the elements of the power set of omega are just the subsets of omega again, right? So all of the single cases, all of the single possible outcomes, 1, 2, 3, all of those are members. So, and because we mentioned that a small p, the probability function, that's going to be a function defined for P omega. So it's going to take elements of P omega, so these guys here, to the real numbers between 0 and 1. It's going to assign a real number to each of these. It's going to assign a real number to this one, to this one, to this one, to this one, etc., right? But there are more subsets of omega. For example, you know, so is this a subset of omega?
Yes.
Right. Very easy to see just visually, right? So 2 and 3 are here, 2 and 3 are in omega. So the same for this one, and so on, right? So we can just write down like every possible combination of things that are here. You know, 1, 2 is going to be a subset, 2, 3 is going to be a subset, 3, 4, 4, 5, but also 1, 2, 3 is going to be a subset, 4, 3, 5. So you know, 1, 2, 3, or some more interesting cases. For example, all the even possibilities for this space, 2, 4, 6. All the odd possibilities, 1, 3, 5, and so on. And then all of these are going to be subsets of omega, but there are also going to be other two couple of subsets which are peculiar, which I mentioned also in the lecture, in the class on basic set theory too. So you need to go check that out if you're not fresh on these subjects. But for example, omega itself is its own subset because it satisfies the definition of subset, right? So the definition of subset again is that A is a subset of B if any element in A is an element of B. So every element of omega is in omega, so omega is its own subset. So that means, for practical purposes, what that means is that since the probability function assigns real numbers to elements of the power set of omega, is going to assign a probability to this set here. And another one of the sets that's going to be here is the empty set. That's also going to be a subset of omega. I mean, that's I guess that's a little bit weird. No doubt about that. That's a little bit counterintuitive. I discussed this also in that class, in the class on relations and functions. The basic idea here is just like once you look at the truth table. So if you look at the truth table that I gave you for implication, and here's like the very short proof that the empty set is in any set, is a subset of any set. So remember that A is a subset of B. If A is a subset of B, that implies that if X is in A, then X is in B. That's an implication of the form if P then Q, right? And if we look at the truth table for P implies Q, we know that an implication is going to be true in at least 3 cases. But one of those cases is the one that interests me here. If the antecedent of the implication is false, so if an implication from P implies Q, if P is false in that implication, in any implication, then that implication is going to be true. Okay, the implication is only going to be false in the case where P is, when an implication from P implies Q is only going to be false if P is true and Q is false, because it cannot be the case that P implies Q if P is true and Q is false. All of that is in the logic and truth functions handout and the logic and truth functions lecture. All of that's there. And all of that information is in the truth table for if then. So that means that implication, that if X is in A, then X is in B, since the empty set is in no set at all, since there's absolutely, it is not the case that X is in the empty set. The empty set has no members. So for that implication, if X is in the empty set, then X is in the in the power set of then X is in omega. We know that X is not in the empty set, so P is false in P implies Q. Therefore, that whole implication is true. Therefore, the empty set is a subset of omega, right? So that's basically a proof, a mathematical proof that the empty set is a subset of any set. But don't worry about it if you don't get if you don't quite get what went down there, I mean, again, you just need to check the truth table for implication, and that's pretty clear. But if it's a little bit obscure yet, that's not going to be on the final or anything like that. But it's important to mention it because uh, it's the empty set is actually going to represent something in a probability experiment as well. Just as the full set omega as a member of P omega is going to represent something, so the empty set is also going to represent something. So the empty set is also going to have a probability, right? So I mean, what could, for example, what does this set represent here? What the probability of what intuitively? So for example, so I guess just to make it a little bit more concrete, what does this set here, the singleton of 5, what does it represent? The probability of that what happens when I throw a die. The probability that what?
That the die will land on 5.
Right, the probability that it will land on 5, right? So the singleton of 1 is going to represent the probability that it lands on 1. The singleton of 2 is going to represent the probability that it lands on 2. The singleton of 3 is going to represent the probability that it lands on 3. So again, I have a die. I haven't thrown it down. I don't know what's going to happen. I don't know what side is going to come up. I know it has to be one of these, right? So this is, again, the possibility space, sample space. I don't know which one of these outcomes here, which one of these possible outcomes will be actualized, but I know it will be one of these. So we have to represent that, right? So we have to represent the probability that each one of these outcomes will be actualized. So the singletons of this, of 1, 2, 3, 4, 5, all of those represent the probability that one of those outcomes will be actualized. So the probability that the probability of 2, 3 here, what does that represent? That basically represents a disjunction. It represents the probability that either that the die lands either 2 or 3. That's basically what it represents. 1, 5 basically represents the probability that it lands either 1 or 5. 1, 2, 3, basically the probability that it lands either 1, 2, or 3. Obviously, I mean, those are not, it cannot land both in 2 and in 3, but what this is representing is just a probability that it lands on either of them, right? So it's going to land on one side. So what's the probability that it lands on either one of these, right? And then it becomes sort of intuitive what this is representing. Any takers?
Is this pretty much saying that the die will land on a number? So it's all possible outcomes?
Right, yeah. So yeah, and basically the idea here is that since I'm performing an experiment with the die, then it necessarily must have an outcome. As long as the future resembles the past, again, that's like one of the assumptions. So it necessarily must have an outcome, right? So since it must necessarily have an outcome, which is going to be one of these, then this represents entire, it necessarily must be one of these. So I know that the probability that it lands on either one of these has got to be 1, right? So that this is what the probability function is going to assign to this. The probability that if I throw a die that has a sample space 1, 2, 3, 4, 5, 6, the probability if I throw it, it lands on one of these is 1, right? It must land on one of them. And the empty set is going to represent like the opposite of this idea, the probability that it lands on neither of these. But again, since I'm already performing an experiment, I'm presupposing that it must have an outcome, right? I mean, unless the future does not resemble the past at all, and the world goes out of existence instantaneously or something like that, in that case, well, maybe then this wouldn't hold. But otherwise, it must have an outcome. So since it must have an outcome, it cannot be the case that it doesn't land on any number, right? So the probability that it doesn't land on any number will be 0, right? So okay, so any questions on that? did everyone follow this? I mean, it's not a problem if you didn't. I can go over something again. It's not an issue at all.
Did you ever say why omega doesn't go over 6?
All right, because because of the specific die we're using. So for example, they have only 6 sides. So it has for example, so I could do another setup, right? Suppose I'm throwing a coin, right? And a coin is either going to land heads or tails, right? So what will omega be? What are the possible outcomes there when I'm throwing a coin?
2.
2 possible outcomes, right? One of them is going to be heads, and the other one is going to be tails. So this will be specifically for the experiment of throwing a coin. So the specific experiment you are performing is going to give you the elements you need to represent the possible outcomes, right? I mean, obviously, these are very simple cases, the coin, the die, etc. But obviously, this gets complicated pretty quickly, but the important point for me, because this is not a probability course, the important point for me is just to talk about. So I guess I should say this. This sort of was a little bit of a logic course, applied logic to writing papers and to writing down arguments and analyzing the logic of arguments. It certainly was that. But in terms of these other ideas of inference, it's just not. We don't just have enough time to go in depth over them. But what I'm interested in right now is to discuss some of these axioms and principles, illustrate how they work as principles of inference, and then look at a philosophical application about rationality. So I guess, and part of one of the claims that I want to make, one of the theses that I want to make, that I will be defending in detail in the next video lecture, will be the claim that a rational person is going to be a person that must satisfy the following necessary constraints or necessary conditions. They have to follow the rules of the laws of logic. So maybe not everyone is rational all the time, but as long as you try to be rational, you must be able to deduce or make inferences following the rules of logic that I have discussed, plus the laws of probability, right? So whenever you are making inferences about some issue which is not where it's not amenable to just a logical treatment, but you only have some evidence that gives you some likelihood, then you should reason according to the laws of probability. So that's sort of like the claim about the rationality here. So, but yeah, going back to the specific question, what set omega is going to be and how many outcomes there are going to be there is going to depend on the specific experiment I'm performing. So there are, for example, let me just mention, for example, that obviously there are a ton of experiments that have very little to do with die or coins. There are natural experiments. So for example, if you have some sort of isotope or whatever, and you want to find out how likely it is that it will decay. So you track, for example, that physical material over time, and you figure out, has it decayed here? Has it decayed there? Has it decayed there? Has it decayed there? Then, and that's sort of going to give you a frequency of how much it has decayed over time, and that's going to sort of give you like some idea of the sample space for that specific experiment, right? By finding out whether in the next second the isotope is going to decay. So that's one example. But for example, another one that's maybe more concrete. There's actually a related video that I want you to watch, like all of you, like 5 minutes of that video, because it's going to be relevant for this. So for example, there's like this video of this guy from the IRS explaining how you're going to, how likely it is for the IRS to audit you, right? When you submit your taxes. And then part of what they tell you is, look, you have 150 million, I think that's the statement, 150 million people send their taxes in tax day, for example, right? And of all of the people who send their taxes, I think it's 0.6% of those get audited. Maybe that's a wrong figure, but just for the sake of argument, assume that that's true. Then that's going to give you what is called a base rate. So that's like the basic probability that in that, in that set, the set of 150 million people, one of them is going to because one of them is going to be audited. But then part of what this tax attorney mentions is that if depending on the income you're making, the likelihood that you're going to be audited increases, right? The higher your income, the higher the likelihood you're going to be audited. So, and that has to do with what is called conditional probability, which I discussed also in the handout. The idea, for example, that if, for example, you know that you are one of the people who sends your taxes, and then you have this other information that maybe you're in a high income bracket, right? So then you have to ask yourself, how likely am I going to be out? Is it that I'm going to be audited, given that I'm in a high income bracket? So that is what is called a conditional probability. And again, these ideas are just the same ideas that we are applying here. It's just the sample space is obviously far more different, and you just cannot. In many of these cases, you cannot find out, for example, the basic probability just by counting. You have to have some sort of frequency at hand. But for example, for the case of conditional probability, for the illustration of those concepts, we can as easily illustrate them in the cases we have been looking at. So for example, suppose that the die lands in either 2, 4, or 6, right? So we throw it down and we know that it lands on either 2, 4, or 6. So I can then ask how likely it is that it lands in 4, for example, right? So, and here's an important difference. For example, in the and here's the basic rule for probability is this one, right? So the basic assignment of probability values in the interval 0, 1 to elements of P omega, so all of these subsets that I have been mentioning, will depend on the ratio, so the proportion of actual outcomes, possible outcomes. So the number of actual outcomes in the relevant element of P omega divided by the number of possible outcomes in omega, right? So how many elements are in the relevant sample, in the relevant event in omega, in relation to the possible outcomes, right? So for example, suppose that I want to find out, again, what's the probability that it lands on 1. So I should then divide, again, number of actual outcomes divided by possible outcomes. So the actual outcomes in that case is 1. I want to find out whether we land on 1. So actual outcomes divided by possible outcomes. So 1 divided by the amount of elements in this set, which is 1 element, divided by the number of elements in this set. So divided by the number of elements in omega. So since it's 1 element in the singleton of 1, and there are 6 elements in omega, the ratio is going to be 1/6. So how likely is it that it's going to land in 1? Well, since the number of elements in the singleton of 1 is 1, and since the number of elements in the possible outcomes is 6, then that probability rule is going to tell us that the likelihood that it lands on 1 is going to be 1/6, right? So it's going to be one of the possible 6 cases. And obviously, because of symmetry considerations, there's nothing special about 1 in relation to 2, 3, 4, 5, 6. We are assuming that the die is fair, it's not loaded or anything like that. So obviously the probability that we land on 2, or it would land on 3, or it would land on 4, or it would land on 5 or on 6 is going to be the same, because again, the number of possible of actual outcomes. So for example, 2, if I want to find out what's the probability it lands on 2, the number of actual outcomes, 2 divided by the number of possible outcomes. So 2, so the number of actual outcomes for it landing on 2 is going to be 1 again. divided by the possible outcomes, so 1/6. But suppose that I want to find out the likelihood that it lands on 2, 4, on 2, given that it lands on 2, 4, and 6. So I know for a fact in this case that it has landed in either 2 or 4 or 6. So I'm asking what's the likelihood that it's going to land in 2. So I have to apply this rule again, but if you notice, here's what I'm asking for is a sort of conditional probability. So given the fact that I know that I can rule out certain possible outcomes, so if it lands on either 2, 4, or 6, then I know that I can rule out that it lands on 1, 3, or 5. So the number of possible outcomes in that case, given that condition, is going to be 3 possible outcomes. And it happens to be the case that 2 is one of those possible outcomes. So again, since the elements in the singleton of 2 are 1, and the elements in 2, 4, and 6 are 3, then 1 divided by 3. So that's conditional on the die landing on either 2, 4, or 6. The probability of it landing on 2 is going to be 1/3, right? So that's an example of conditional probability applied to this very simple case. Conditional probability just means that you have this other information, these other new conditions, which might alter the size of the sample space, for example. So yeah, I mean, I guess I want to ask if there are people who will be willing to meet, to at least try to meet next week, both on Monday and on Wednesday, so that we can finish covering the this material and the material on representation. I'm going to send you a link, and I hope some people will show up to those, both to Monday and to Wednesday at the usual time, at the time for this class, you know, the 10:15 a.m. Sorry, 11:15 a.m. I'm in a different time zone, so 11:15 a.m. for people in Amherst. So I'm going to send you that link, and in either case, I'm going to try to record for people who can't show up, but I hope some of you can, just so that we can finish some of the course material, because it's very important for me that we try to focus on some of the applications of these to philosophy of rationality, and we're not going to be able to do that if we don't have this couple of extra live meetings. But yeah, I mean, I guess we have run out of time for today, but yeah, any questions, email me any questions, and I'll send you a link for Monday and Wednesday. Thank you.
Thank you. Have a good day.
Thank you.
You too.
Thanks. See you Monday.
Thank you.